Test, mic test. If you hear me, please just type 1. Excellent. Two minutes and we will start. We said we'll give 5 minutes for people to attend. So we'll start in 5 minutes, inshallah. Hello Arsalan, sorry for making you wait everybody, but we just need to give some time for people to attend. I know it's a little bit hard because of the internet connection for some people, so just be patient with us. Thank you very much. What about now? The sound is okay or the sound is bad? Little noisy. Sorry. Maybe because of your internet connection. Okay, I'll try to make the mic away from my face, so maybe it will be fine. shall we start or just wait a little bit more? If we wait, type 1. If we start, type 2. Okay, 1 minute and I will start. Whether we have 20 or we have 9, I will start. Okay? Okay. Mic test, mic test. Do you hear me well? If you hear me, please type 1. Okay, guys, now it's 10 minutes since we started. Should we start now? Because we don't need to make other people just waiting and we don't know when they will join us. Um, is there some problem with the sound? Because I feel it's okay. Everybody typed 1. Okay, guys, let's start. Bismillah ar-Rahman ar-Rahim, by the name of Allah. We'll start our lecture today. Sorry, this is the first time I use this program, so if we have some technical issues, please accept my apologies. So today we'll talk about the basic radiation safety, BRS. First, let's start with the history of radiation. So 79 AD, first known human use of uranium. Roman artisans produced yellow-colored glass in mosaic mural near Naples, Italy. 1925, suspicious developed around watch dial painters or jaw lesions. Dentists diagnosed lesions as jaw necrosis due to radium deposits in jawbone. Doctor noticed bone changes and anemia in dial painters. So this photo shows dial painters. They used to use a brush and with their tongue, and then they paint the inside the swatch, and this developed anemia later on. So in this diagram, we see electromagnetic radiation spectrum, and it's divided into two parts. We have the ionizing radiation part, where we have the gamma rays and X-rays, and you can see the frequency is very high, and we have very short wavelength. Whereas in the other side, we have the non-ionizing radiation. Example, we have the ultraviolet, visible, infrared, microwave, and radio wave, where we see the wavelength is very long. So in this slide, we'll talk about the types of radiation. So we have the radiation is classified into two main categories. We have the non-ionizing radiation, which cannot ionize matter, and we have the ionizing radiation, which can ionize matter. The ionizing radiation is classified into two types: directly ionizing radiation, which is the charged particles. Examples, electron, proton, alpha particles, and heavy ion. Whereas the indirectly ionizing radiation, we have the neutral particles like photons, X-ray, gamma ray, and the neutron. This is the international sample of ionizing radiation, and I guess every one of us is aware of this sample. The next slide will talk about the uses of ionizing radiation. So we have radiation used in science, in carbon dating to determine age, in power satellites, and used in medicine for diagnosis and treatment of illness, sterilization, and used in industry for smoke detectors and food preservation. Could not hear the voice. Karawan, I think my voice is clear. Do you hear me now? I think the sound is okay because everybody is saying it's fine. Okay. Please type 1 if sound is okay. Okay, fine. So let's talk about the nuclear notation. So if we have an X, which is the chemical sample of the element, so the constituent particle forming an atom are proton, neutron, and electron. Protons and the neutrons are known as nucleons, and they come from the nucleus. The atomic number, Z, the number of protons and number of electrons in the atom. Atomic mass number A, which is the summation of the protons plus neutrons, or the number of nucleons, where Z is the number of protons, atomic number in an atom, and N is the number of neutrons in an atom. Radioactive sources. So we have a lot of radioactive sources around us. We have radiation coming from the solar radiation, consumer products, radioactive waste, nuclear medicine, X-ray, radon, cosmic ray, among each other, nuclear weapons, and so on. Now we'll talk about natural and man-made sources of radiation. So if we have this pie diagram, so we have the radium gas that constitute 50% of the source of radiation around us. The external radiation forms 25%, the internal radiation forms 10%, and the man-made forms 15%. The radon, external and internal, it's natural radiation and it's form 85% of the total radiation, whereas the man-made forms the 15%. Okay, I will make the mic as close as possible. This is good? Okay, fine. So the average annual radiation exposure from all sources equal about 2.8 millisievert per year. This is according to the US, by the way. So the natural radiation, 85% of overall radiation exposure consists of external, which is coming from the cosmic, mostly from the sun, 12%, and terrestrial from the ground and buildings around 13%. The internal from indigested radioactive nuclides from food, such as potassium-40 or K40. Radon emanating from the ground, and it is an alpha particle emitter. Half-life of radon is 3.8 days. So this is the natural radiation forming 85%. So we are remaining with 15%, which is the man-made. So the man-made, which is 15% of the overall radiation exposure, consists of medical exposure, which is 90%, consists of external exposure, example from X-ray unit, occur in radiology and radiotherapy departments. Internal exposure after administration of radioactive isotopes occurs in nuclear medicine department and research laboratories in a hospital environment. In brachytherapy, typically sealed sources are used. The risk of internal exposure is minimal. Non-medical exposure, 10%, consists of army research, fall-off weapons, and so on. However, depending on lifestyle and location where one lives and work, variation between 1.5 millisievert per year and 5 millisievert are normal. Medical exposure is not included. Now we'll have a small question, and we ask you to participate in answering this question. Example: if the average exposure in a country A is 3 millisievert per year and country B is 1.5 millisievert per year, calculate the annual occupational exposure. And I will ask you to participate. Just let me give you the question. Please vote. have 3 voted till the moment. 4. Okay, 5. Half of you, we are 15 and only 7 voted. Come on guys, this is very simple question. We are not yet in the hard questions. The hard questions are coming. The sound is low. I think it's fine. Don't worry, I'm not catching your name. I just need you to vote. Whether you know or you don't know, just vote what you think of. Still 7 more. We are 10. No harm, just a try. Okay, 11 voted, so at least we are half of the people, more or less. Okay, so let's see the answer. So country A, 3 millisievert per year plus 20 millisievert per year. This is your annual exposure. So the total is 23 millisievert per year. For country B, 1.5 millisievert per year plus your occupational dose 20 millisievert per year. So the answer is 21.5 millisievert per year. So if you answered correctly, put 5 marks for yourself. Okay, let's move on. So sources of radiation. Let's see some photos. How to calculate? Why did you add? Because you're okay. The 20 is 20 millisievert. This is your occupational dose as a radiation worker. This is from the regulations. It's 20 millisievert per year as a radiation worker, according to the ICRP and NCRP. Radiation workers. The public is 1 millisievert per year. Okay? So let's talk about MID radiology. What devices they do have? They have X-ray emitted from the X-ray tube in various equipment for diagnosis of disease. They have the X-ray room, the CT scanner, portable X-ray machine, mammography, portable fluoroscopy, angiography, and fluoroscopy machine. So this is, you can find it in diagnostic radiology or MID radiology. It depends on the name in your country. Let's take another department. Let's take the nuclear medicine department. What they have. So they do have radiopharmaceuticals injected into patients for imaging with a gamma camera or PET scanner, treatment of diseases such as thyroid cancer. So this is the vial, and here we have, they are injecting the radioactive material, and here we have the hot lab, And this is the body where they inject the radioactive material to do the imaging for the patient. And this is the pit. So the source of radiation in nuclear medicine is the patient, okay, whereas in other departments is the machine. Let's take another department, radiation oncology or radiotherapy. So they use X-ray, gamma ray, and electrons for various equipments for treatment of diseases. This is linear accelerator, this is a brachytherapy suit, and this is intraoperative or IORT. The blood bank, they are using cesium source for blood products irradiator, and this is the device. It's gamma rays from a blood irradiator. Let's talk about the international organization. During the early years of diagnostic radiology, a large number of severe overexposures and radiation accidents occurred. A growing number of acute radiation exposure incidents led to recommendations on radiation protection in the internal literature. The International Commission on Radiological Protection, ICRP, has established fundamental radiation protection principle and recommendations. The International Commission on Radiation Units and Measurements, ICRU, the ICRU and the ICRP were established in 1928 by the Second International Congress of Radiology. The ICRP is a non-political organization. Its members are elected on the basis of well-recognized work in radiation protection and related fields. We'll talk now about the principle of radiation protection. It seems there's some connection problem. Just wait a second, please. Do you hear me now? Is there a sound? If you hear me, just type 1. Do you hear me? Type 1, please. The general purposes of radiation protection are to prevent deterministic effects such as arrhythmia, cataract, and so on. Limit. I have no voice. Okay. Everybody hear me, please? Okay. Fine. Excuse me, guys. It seems some internet connection in your area is not good, so sometimes the sound fade out. I have no control in this. I'm sorry. Limit the probability of stochastic effects such as cancer and hereditary effects to levels deemed to be acceptable. The fundamental principle of radiation protection are 3 main things: justification, optimization of protection, and dose limitation. The 3 exposure situations. This is very important to know it. Planned exposure situation, a situation of exposure that arises from the planned operation of a source or from a planned activity that results in exposure from a source. So this is we planned for. So the patient is coming to take radiation. Okay, we planned for this. So the patient have a treatment planning for this. Emergency exposure situation, a situation of exposure that arises as a result of an incident. Of accident, a malicious act, or any other unexpected event,
and requires prompt action in order to avoid or reduce adverse consequences, like if you have a radiation spill. So this is emergency. We don't have control on that. Existing exposure situation, a situation of exposure that already exists when a decision on need for a control needs to be taken. So this is the main three exposure situations. Principle of radiation protection, justification. So any decision that alters the radiation exposure situation should do more good than harm. So if we want to treat a patient, we have to justify why we want to treat. And the treatment should give the patient benefits more than harm. So if you want, let's say, if a patient coming with a brain tumor and you want to treat, you should not make him blind. You try your best to avoid this. All applies to three exposure situations. Second one is the optimization. The likelihood of incurring exposure, the number of people exposed, and the magnitude of their individual doses should all be kept as low as reasonably achievable, the ALARA principle, taking into account economic and social factors. Also applies for the three exposure situations. The process should be constrained by restrictions on the doses to individual and the risk to individual. The third one is the dose limitation. The total dose to any individual from regulated sources in planned exposure situation other than medical exposure of patients should not exceed the appropriate limit specified by the Commission. As we said, for you as a radiation worker, you should not take more than 20 millisievert, let's say, per year. Is there anything, Mr. Jalal? Okay. Dose limitation only applies to planned exposure situation. Are aimed to ensuring that no individual is exposed to radiation risks that are judged to be unacceptable. Differ depending on whether the exposure is to workers or to the member of the public. So as we said in the previous example, as a radiation worker you are allowed to take 20 millisievert per year, whereas the member of the public is not allowed to take more than 1 millisievert per year. We'll come to this in the later slides. Do not apply to medical exposures where the issue is intended result in terms of diagnosis or treatment. So we cannot say, like a patient have cancer, the maximum dose for as individual is 1 millisievert, but now he's coming into a radiation therapy department, so he need to be treated, let's say, by 20 gray or 40 gray or 60 gray, depends on the tumor location. We cannot apply the rules on the medical exposure. Okay? The ALARA principle, I think all of us know this. ALARA is acronym for as low as reasonably achievable. This is a radiation safety principle for minimizing radiation doses and releases of radioactive materials by employing all reasonable methods. ALARA is not only a sound of safety principle, but it is the regularity requirement for all radiation safety programs. Let's talk about the basic ways for radiation protection from radiation. So we have the time, distance, and shielding, and RP stands for radiation protection. So less time spent near source less radiation received. So it means that if we have less time near the radiation protection is better. Okay, less time, better radiation protection. Distance. Greater distance from source, less radiation received. So the distance, how much far we are from the radiation, the better the radiation protection for us. Behind shielding from source, less radiation received. As we see, this man is receiving less dose because of the shielding in ahead of him. And the shielding have some question mark because you have to shield properly. So shielding is dependent on type of radiation you want to protect against. For gamma and X-rays, usually use lead and concrete, but for neutrons, you need something rich of hydrogen like wax or paraffin. That's why they add to the bunkers where we have high energy, machine like above 10 MV, they use wax or paraffin or wood to make the fast neutrons as slow neutrons and so on. Let's talk about the time. The radiation dose is directly proportional to the time spent in radiation. Therefore, a person should not stay near a source of radiation any longer than necessary. If a survey meter reads 4 milliroentgen per hour at a particular location, a total dose of 4 milliroentgen will be received if a person remains at that location for 1 hour. Because we have 4 milliroentgen per hour, so if he stays for 1 hour, he will get a dose of 4 milliroentgen. In a 2-hour span of time, a dose of 8 milliroentgen would be received. The following equation can be used to make a simple calculation to determine the dose that will be or has been received in a radiation area. All of us know this. So the dose equal dose rate multiplied by the time. Let's take an example and I'll ask you to participate in this poll. A technician is an area for 10 minutes and the reading of the survey meter is 5 milliroentgen per hour. What dose of radiation does the technician receive? And let's participate in this role. Just a second. Okay, here we are. Please, let's do it fast. We don't need to spend much time in simple questions. Let me move it just to make it clear. Okay. Come on guys, 14 out of 21 participated only. 16. Okay, so let's see how we could solve it. It's straightforward, very easy. So 5 milliroentgen per hour divided by 60 minutes per hour. So this is to convert from 60 minutes to hour. So we got 0.0833 milliroentgen per minute. Just multiply this one by the 10 minutes, and then we got how much dose this guy will receive. So 0.0333 milliröntgen per minute multiplied by 10 minutes, this is equal to 0.833 milliröntgen total dose. If you got it, put 5 marks for you. If not, we'll see. Okay, let's continue. Next question. Example 2. A technician wants to receive no more than 1 milliröntgen dose, knowing that the above conditions. What is the maximum time the technician can stay in the area? So he wants to receive maximum 1 milliröntgen. For how long? I'm asking the time now. For how long he can stay to achieve this from the previous example? Let's have it. Number 3. Okay, here we go.
At least half of you should participate, then we can continue. 8 out of 22. Not yet. We need more. Okay, fine. Let's answer this question. So 1 milliröntgen divided by 0.033 milliröntgen per minute. So the maximum time he can stay is 12 minutes. Okay, let's move on. Now let's talk about the distance. Increasing distance from the source of radiation will reduce the amount of radiation received. A radiation travels from the source, it's spread out, becoming less intense, like fire, or like we could say the same. So if this is the radiation, if we are away a distance x, so we have the dose here equal to 1. If we are double the distance, we have the dose 1 over 4. If we are 3 times distance, so the dose is 1 over 9. This is analogous to standing near a fire. The closer a person, if you answer correctly, give yourself 5 marks. Sorry, you are asking about the percentage. Okay, I will show it later, okay? The closer a person stands to the fire, the more intense the heat feels from the fire. This phenomena can be expressed by equation known as the inverse square law, and I guess all of you heard about it, which states, as the radiation travels out from the source, the intensity decreases inversely with the square of the distance, and this is the equation. So the inverse square law, sorry, there is some samples not coming correctly, this is multiplication. So I1 multiplied by x1 squared equal I2 multiplied by x2 squared, whereas I is the intensity and x is the distance. Let's have another roll. Number 4. The intensity of radiation is 530 Röntgen per hour at 5 feet away from a source.
What is the intensity of the radiation at 10 feet? Let's vote. Come on, guys. Inverse square law. We need 4 more to okay, here we go. So fine, we have 14 voted, so we have 9 got the correct answer and 5 did not get the correct answer. By the way, I can know the names, okay? So I know who answered correctly and who did not answer correctly. Okay, let's see how we solve it. So I2, this is the intensity that we are looking for, equal I1 multiplied by x1 squared divided by x2 squared. Very simply. So we just substitute I2 equal 530 Roentgen per hour multiplied by 5 feet squared divided by 10 feet squared. And this is equal to 132.5 Roentgen per hour. Okay. As I promised, the guys, the first 3 guys, they will have gifts. And I can know this from the roll. Okay? Fine. Let's continue. In this instance, the distance has been doubled and the intensity at that point has decreased by a factor of 4. Let's talk about the shielding. I'm here trying to put the 3 departments. So this is the first lady, she's putting the apron. This is from diagnostic radiology. And then here we have the nuclear medicine department, and here we have the radiation therapy department. Shielding significantly reduces radiation exposures. Dense material generally absorb the most radiation. That's why we use lead. Equipment is designed with a built-in radiation shielding, and we can see this in the second image in the container. It's already lidded and the radioisotope is inside to protect it from the people who are working. Rooms with radiation sources will have shielding installed in the walls. That's we see in the radiation therapy department, and also we can see it in the diagnostic radiology. They are putting shielding even in the glasses when they are doing imaging for the patients. Oh. There is some problem. Just a second. Yeah, I think we are fine. So personal radiation protector devices may be required for some stuff. Shielding for different types of radiation. So if we have ionizing radiation and we have alpha particles, how far the alpha can go. I think the animation is not working properly. Anyhow, we can see it from the, okay, sorry. Anyhow, the alpha particles stopped in a piece of paper can stop the alpha particles. The beta can be stopped in a plastic. The gamma rays are stopped in a lead. the neutron are stored in the concrete, and because it's rich of hydrogen. Equipment shielding. What's in air? I did not catch up. You are talking about the neutrons? Yes, I'm talking about in air. They are moving in air, and then we are putting a shielding in the head of each. Okay. Equipment with radiation sources must have built-in radiation shielding that follows national and international standards. And like this one, this is an image of an X-ray tube head. You see the shielding around. Built-in shielding is tested when a new equipment is delivered to our hospital by a qualified physicist or in your hospital. Examples: the X-ray tube, the HDR remote afterloader for brachytherapy, radiotherapy treatment unit head, and CT simulator or CT. The room shielding. Room shielding is designed prior to construction and verified after equipment installation and before clinical use. And this is a radiotherapy facility, and you can see the maze, and all the walls are very thick to protect against the primary and secondary radiation. In some situations, room shielding design must be approved by a regulatory body. Room shielding may be tested annually. That's why we do a survey for the room to make sure that we don't have leakage, we don't have any problem with the rooms. Sure, we can have this later on. Some of us could present about shielding calculation and design. This no problem. This is a very nice idea, Karwan. Thank you. HVL layer HVL. A HVL layer HVL is defined as the thickness of absorber necessary to diminish the intensity of radiation to half of its initial strength. So we have the HVL and the percentage of reduction. The first HVL reduced the intensity by 50%, the second one by 25%, third one 12.5%, fourth 6.25%, and so on. The relation between HVL and TVL. HVL HVL layer, TVL 10th value layer. TVL thickness of attenuating material that decreases beam intensities to 10% of its original value. The TVL equal 3.32 HVL. How it comes? From ln 2 over ln 10. You got this equation, and vice versa, 3.32 HVL. And this is a table showing radioisotopes for cesium-137 and cobalt-60. And we have the HVL and we have the 10th val layer. Like for concrete, the HVL is 4.8, whereas the concrete 10th VL is 15.7. Very important notice: for radiation protection purposes, we use the maximum energy of the radioisotope, or at least the average one. Like for cobalt, we have two energies. We have 1.17 and 1.33. When we are doing the calculations for shielding, we consider either the 1.33 is the maximum energy that's coming outside, or at least 1.25, which is the average energy for the two energies coming from the cobalt-60. And you must overestimate your calculation. So let's say if you need 50 centimeter of concrete, usually you add more, like 70 or add 80, and so on. So you try to overestimate. So this one will reduce your annual dose as maximum as possible. Let's talk about radiation quantities and units. This is very nice sample. I like it in one of the books. So the activity in becquerel is coming from radioisotopes like sun, And then if it travels in air, we have it became as exposure, which is coulomb per kilogram of air. And then if it's come inside the body, we call it absorbed dose, and the unit is gray. And then if it affects the tissue, and because of different types of radiation, we have different WR, which is the weighing factor, so it became a sievert. Then if we want to consider its effect on the body itself with the tissue, it become effective dose. So the activity, the rate of decay, or the number of nuclei of a radionuclide decaying per second is known as the activity. Yeah, I'm fine. 30 minutes, we'll move on some certain, some slices we'll move on fastly. Thank you, Muhammad. So the activity is the donation is dN by dt. dN is the number of photons you have, and dt is the time. And the SI unit of the activity is becquerel. And 1 becquerel is equal to 1 disintegration per second. The older classical unit is the Curie, stated for Maria Curie. And 1 Curie is the activity of 0.980 gram of radium equilibrium with its daughters. And 1 Curie is equal to 3.7 10 to the power 9 becquerel, and it's equal to 3.7 10 to the power 10 disintegration per second. This is square, it's multiplication, but I don't know why it's not coming properly in the presentation. Okay, what is the activity in both becquerel and Curie for a source emits 7.4 10 to the power 9 photons in 3 minutes? Let's have another roll. This is number 5. So let's publish. Yeah, let's do it. Come on, guys, straightforward. Five votes only out of 20. Just give me the activity in Curie. It's not a problem with in becquerel. Just get it in Curie. Two more to go. We are 8. Nine. Okay. I don't want to tell who answered correctly and who did not. Anyhow, let's solve it. So A equal dN by dt, and equal 7.4 10 to the power 9 photons divided by 3 minutes multiplied by 60 seconds. This equal to 41.1 megabecquerel, and now we convert it into Curie. So 41 10 to the power 6 becquerel divided by 3.7 10 to the power 9 becquerel per curie, and this equal to 1.11 millicurie. So we have how many ones answered? So we have like 37% of the people answered correctly out of the rest. 30%, not bad. Okay, let's move on. The half-life, T-half, time required for substance to lose half of radioactivity. Every radionuclide has a unique half-life, range from less than 1 second to billions of years. The general formula for activity A equal A0 e to the minus lambda t, where A is the activity after time t, and A0 is the initial activity, or at t equals 0. Lambda is the decay constant, and it's the unit of t minus 1. I mean time minus 1, like second minus 1, year minus 1, wherever. And t is the decay time. And we have the half-life, t half equal ln 2 divided by lambda. Ln 2 is 0.693. Okay, let's have this question. This is number 6. Okay. A container has initial activity of barium 137 metastable state equal to 100 millicurie. If the half-life of barium 137 metastable state is 2.55 minutes, what will be the final activity after 15 minutes? Okay, we are getting people who are answering fast and right. Mhm. I increased the time a little bit for like 30 minutes more because I guess we are doing very slow. Anyhow, we are 10. We could answer the question. Okay, so the solution. Half-life T half equal into over lambda, and lambda equal into over T half, which is equal to 0.693 over 2.55 minutes. This is equal to 0.272 minute minus 1. Then substitute in the equation. E equal E0 to the minus lambda T, 100 millicurie, e to the minus 0.27. This is equal 1.69 millicurie. I see the guys who answer after I showed the answer. Okay, no problem. At least we are solving it. Okay, let's go on. Exposure. And this is William Röntgen. I think everybody knows who's William Röntgen. The quantity exposure describes an X-ray or gamma ray field. It is a measure of the amount of ionization produced in air by the X-ray or gamma ray. Exposure is defined as amount of charge of either signs, I mean positive or negative, produced by X-ray or gamma ray in 1 kilogram of air, when all charges, positive and negative, are stopped in the air. It comes in the sample X equal dq by dm. The SI unit is coulomb per kilogram, and all the classical unit, all of us know it's the Röntgen. And 1 Röntgen equal 2.58 10 to the power minus 4 coulomb per kilogram. we have three main limitations for the exposure. The first thing, applicable only for X-rays or gamma rays, only. So it doesn't apply for charged particles. Next, applicable only for air, no other material. So we cannot say we have exposure inside the body. We cannot say we have exposure inside that material. It's only in air. And third one, cannot be measured for high photon beams. Okay, this is very important. Limitations for the exposure. Okay. There is a very nice formula to calculate the exposure. So the exposure X equal 10 milliröntgen multiplied by MAS. We know the MAS, all of us, I think. Divided by R squared, this is distance, multiplied by KVB over 100 squared. So by this equation, if you have the MAS for the machine and the KVB, you can directly estimate what is the exposure at that location. The exposure X is linear proportional with the tube voltage KVB to the power 2.07. We approximated to 2. When KVB increases, the exposure also increases to the power of 2. And we see this in the equation. So the KVB increases by 2, then all the exposure is increased by 2. The exposure is linear proportional with MA and MAS, milliampere and milliampere second. If MAS is constant, the exposure is constant, whether MA or the time is or are changed. Okay? The exposure X is linear proportional with the inverse square value of the distance from the X-ray source. As we seen in the previous slides, the inverse square law also applies here. The further the distance, the lower the exposure you receive. Let's have another question, or two more questions. This is number 7. Okay, let's publish it. Okay. Calculate the exposure for the following machine parameters: KVB 80, MAS 3, R 50 cm. If you would like, I can show back the equation, so it will be easy for you to answer. One correct, one wrong, 2 votes. 4 votes. 6 votes. 8. We need more, maybe another one, and we could stop. 9. That's it. Okay. So let's solve it. So we got more or less 40% of you answered correctly. So we come to this equation: exposure equal 10 MR MS over R squared, KVB over 100 squared, and we got 76.8 milliröntgen. Okay? Let's have another question. Which is number 8. Calculate the exposure for the following machine parameters: KVB 120, MAS 3, and R equal 50.
7 votes. We need another 2 more. 8. Another one. Okay. So the answer is 172.8 milliroentgen, and we got more or less 40% of the people answered correctly. Let's see how we solve it. So directly 10 MR multiplied by 3 over 0.5 squared multiplied by 120 over 100. This is equal 172.8 milliroentgen. Okay. Let's move on. Absorb dose, any medium, any type of radiation, not as the exposure. Exposure only in air, and only for what? For photons and X-rays. It doesn't apply for charged particles. This is Harold Gray. So the absorbed dose D is defined as so we have energy deposited in a mass. So D equal dE by dm. E is the energy and m is the mass of the material. dE is the mean energy imparted to a matter of mass m. The SI unit for the absorbed dose is 1 joule per kilogram, and its special name is the gray. So the SI unit is 1 joule per kilogram, but the special name is gray. And I think most of us using in their department the gray. The older unit of absorbed dose is the rad, representing 100 erg per gram, or 1 gray equal 100 centigrade equal 100 rad. What does rad stand for? Anyone knows what rad stands for? Excellent. Radiation absorbed dose. Thank you, Sevji. Okay. Rolf Sievert. This is the equivalent dose unit. Equivalent dose is the quantity which takes into account the effect of radiation quality, which relates to the degree which the type of ionizing radiation will produce biological damage or harm. Equivalent dose is obtained by multiplying the absorbed dose by a radiation weighing factor. The quantity is independent of the absorbing material, i.e. the tissue. There's some problem. It should come the equation here. Anyhow, so the equivalent dose equal the dose multiplied by WR. Yeah, it's coming here. So this is the equivalent dose equal WR multiplied by the dose. WR is the radiation weighing factor. H is the equivalent dose in sievert. The SI unit is the sievert. The old unit is rem. What's rem stands for? Radiation equivalent man. Thank you, Muhammad. Okay. We have super active guys. Slowly? Okay. I will go slowly. The absorbed dose deliver the radiation type R averaged over a tissue or organ T in gray. WR, the radiation weighing factor for the radiation type R. Radiation weighing factor WR is dimensionless number. WR usually greater or equal to 1, which depends on the way in which the energy of radiation is distributed along the path through the tissue.
The ICRB 103 in 2007 established a new report for radiation protection, and this is for neutron. Neutron no longer became discrete, it became as a function of energy. And we have the radiation type, we have photons and all energies, WR equal to 1, electrons and muons and all energies equal to 1, neutrons continuous function of energy, it ranges from 2 to 20, it depends on which energy you have. Protons and charged pions 2, alpha particles, fission fragments and heavy nuclei is 20. What does this mean? The slide did not change with me. Okay. Everybody is seeing the correct slide? If you are seeing the correct slide now, please type 1. Thank you very much. Okay. So what does this WR mean? If we have a radiation type photons and we have radiation type alpha, so the alpha give 20 times hazards more than the photon radiation, or protons give double the hazard rather than the photons, and so on. Example. So this is example number 9. Okay. So let's go for number 9. A person has absorbed an alpha particle dose of 0.2 milligray. Calculate the equivalent dose, giving that WR for alpha equal 20. All of us should answer correctly. Please, don't disappoint me. Okay, we have 50% people, 11. Okay, we'll give 10 seconds, then we start to answer. Okay, let's answer it. Straightforward. So we have H equal D multiplied by WR. D is 0.2 milligray multiplied by 20. The answer is 14 millisievert. Only one voted wrongly and the rest was fine. So 1 out of 15, this is fine. Okay. What do we really need to know about this WR and all this stuff? 1 Röntgen equal almost 1 centigrade, which is equal to 1 centisievert. For gammas and betas, 1 gray equal 1 centisievert. 1 centigrade equal 1 centisievert. For alpha, neutrons and protons, 1 centisievert equal 1 centigrade multiplied by Q. Sorry, maybe the slides is messed up. I don't know, the program did not make it well, but at least you could hear me. So for alpha particles, the neutrons and protons, it doesn't mean that 1 centisievert equal to 1 centigrade directly. No, you should multiply by a quality factor of the radiation. This is a summary of radiation quantities and units. We have the quantity, the equations, and all this stuff. I will not go into details because we already talked about them. Radiation worker and public. A radiation worker, a person who works in an area where he or she may receive a radiation dose above the background. Radiation worker must be educated in radiation safety. The personal radiation dose for all radiation workers is monitored with a personal dosimeters like TLD badge. Examples of radiation workers. So we have the physicians, radiographers, nurses in radiation area, physicists, and so on. And all other people who working in hospital, working wherever, or coming for visits or whatever, they are considered as members of the general public. Anyone out of these 4 or 5 categories that we have is considered as member of the general public. The exposure limits from NCRB report. NCRB, this is the national, this is from US. Report number 116, and ICRB is the international. And most of the people are following the ICRB. And that's why written here used. So the effective dose annual, the NCRB is giving 50 millisievert, where the ICRB they are giving 20. The effective dose cumulative 10 multiply the age in year, whereas the ICRB 100 millisievert in 5 years, and so on. I will not go in the table in details because it's there in the reports, and you can easily read it. Detection of radiation. Radiation is colorless, tasteless, smellless, soundless, invisible. So how can we detect it? So we have detection mechanisms. We have ionization, release of ion pairs by radiation. We have chemical, release of free radicals in a solution. We have temperature, rise from deposited energy. We have scintillation, light flash in a special phosphorus. And thermoluminescence, light release on heating a phosphor. There is some connectivity problem, I don't know. Just a second, please. ICRB changed dose to 20 millisievert, taking into consideration the brachytherapy. Yes, you're right. You're right. Yes, you're right. Radiation detectors, the gas-filled radiation detectors, we have ion chambers, proportional counter, Geiger counter. The liquid scintillation radiation, and solid detectors, we have scintillation counters, semiconductors like HBGE and CDTE, germanium. And this is very famous characteristic curve, and all of us should know it. It starts with the IC, the ion chamber area, and then we have PC, proportional counter, and we have the GM. This is the main 3 areas. We have here the saturation area, and here we have the shoulder. I will not talk about it, they are not important, but for me, the 3 main areas, very important: ionization chamber, proportional counter, and GM. Detection efficiency. The efficiency or sensitivity of a radio detector is a measure of its ability to detect radiation. Efficiency of detection system operated in a pulse mode is defined as the probability that a particle or photon emitted by a source will be detected. So what's the equation? Efficiency equal number detected over number emitted. Let's take the last question. Okay, I'm asking you to calculate the detection efficiency of a GM detector if the number of emitted photons equal 1 10 to the power 9 photons per second, and the number of detected photons equal 1 to the 10 to the power 8 photons per second.
8 out of 21. We need more 3. Two more. Okay. We are 10, exactly half. One more and we stop it. Fine. So most of you answered correctly. It is 10%. So how we solve it? So efficiency equal number detected over number emitted. 1 10 to the power 8 divided by 1 10 to the power 9, which is equal 0.1, which is 10%. Okay. Personal monitoring devices, PRMD. A personal radiation monitoring devices is a radiation sensor designed to measure over a specified period of time the radiation dose received by a person who's occupationally exposed to radiation. Choice of monitoring devices depends on for dose rate or contamination purposes, why you need it, high or low levels, particles or photons, energy of photons, required accuracy, and choice of detector type. May be important for you to check the following things: required sensitivity, otherwise not so important. The design of the instrument to fulfill the requirement is more important. So we have different types. This is the ring one. All of you, I think, this is the TLD, this is personal dosimeters, and this is the bucket dosimeters. I think all of you know this. The optimum KVB techniques. So KVB determine the quality of the beam. X-ray penetration is governed by the KVB settings, as we seen in the exposure equation. KVB controls the contrast of the radiographic image. Contrast is the difference in the density of the adjacent structure on the image. KVB and density of the body part impacts the amount of scatter radiation. High KVB, more scatter, equal low contrast, more penetration. So you have to choose your KVB according to what you are looking for. If you are looking for a low contrast, then you can use the KVB. If you are looking for more penetration, as patient is obese, you need to use higher KVB. Lower KVB, less scatter, high contrast, less penetration. For superficial or thin patient, you can use the lower KVB. Optimum KVB, consistent scatter, adequate contrast, and sufficient penetration. You don't want to overexpose the patient, and you don't want to underdose the patient. You don't need to lose the image quality. You should work in an optimum KVB. That's why most of the machine have AAC control. Optimum KVB is based upon the area of the body and the film size to assure adequate penetration. Technique selection and KVB adjustment. So adjustment the KVB and MAS is a balancing act. When KVB is increased, MAS must be decreased. We are balancing both density and contrast of the image. If KVB is increased without reducing the MAS, penetration increases and the contrast is reduced. Over-penetrated images lack contrast and have high density, became more black. Under-penetrated images have very high contrast with dense structures not being penetrated white. The higher the KVB used, the less interaction the photons will have with the tissue being exposed. When we increase KVB by 10, we reduce the exposure by about 25%. Use as high as possible KVB that will provide adequate contrast.
Now we'll talk about the biological effect of radiation. So the radiation causes ionization of the atoms, which will affect the molecules, which may affect the cells, which may affect the tissue, which may affect the organ, and it will lead to effect in the whole body. What radiation affects? Directly or indirectly, radiation affects the DNA. So this is the most important thing. DNA is the most important thing in the cell. DNA controls the cell function and ability to reproduce. Possible effects: what if radiation strike the DNA? What will happen? It will either destroy the DNA, which will cause the kill the cell, damage the DNA, and then the cell can have two things: repair itself, which is most likely, or not function or function improperly, or undergo uncontrolled division, which will cause cancer. Other damage to the DNA: many other entities cause breaks in the DNA, temperature, chemicals, and so on. Human DNA suffer millions of DNA breaks daily, but by God, well, most of them are repaired automatically. So direct effects of molecule by ionizing or excitation, by ionization or excitation of the molecule, and subsequent dissociation of the molecule. So we have, this is the normal DNA on the most left side. Gamma or beta radiation is striking the bounds in the DNA. High energy proton from fast neutrons or collision, you see, most breaks the DNA. Alpha particle, because WR is 24 alpha, you see, it's totally destroy the DNA. Severe damage, here we have heavy damage, and we have moderate damage with the gamma or beta. Let's talk about the chromosome and the chromosomal structure. So this is our chromosome. Conventional numbering system of the G band in the human chromosomes. So this one is called one chromosome unduplicated. Then this is duplicated. This one is called, this part is called the telomere. Telomere means the fast, or what they call it. I forget the. Okay, anyhow, it's the furthest part of the chromosome is called the telomere. This is called the chromatid. Sound is okay? Type 1 please, if sound is okay. It seems your connection have something, because most of the guys are typing 1. Okay. The chromosomal damage. So chromosomal aberration, breaks and incorrect rejoining before the chromosome material has been duplicated, unstable, lethal to the cell, and do not pass to pregnancy, implication, and this is called the cell killing. What types of chromosomal aberrations? We have the breaks, fragments, we have rings, dicentric, anaphase bridge. I will not talk about it in details because this needs much more time. Breaks and incorrect rejoining after the chromosome material has been duplicated. This causes stable, persist for many years, non-lethal to the cell, and pass to pregnancy, and implication alteration in genes. Examples: translocation, inversion, deletion, and duplication. This is very important things that you have to know. The risk terms, what do we mean by acute, what do we mean by chronic, stochastic, non-stochastic, somatic, genetic, and teratogenic. So acute is a large dose of radiation in a short period of time. Chronic, small doses of radiation protracted over a long period of time. Stochastic, health effects that occur randomly and for which the probability of the effect occurs rather than the severity is assumed to be a linear function of those without a threshold. Non-stochastic, health effects which does not appear until a threshold value is exceeded and for which the severity of the effect increases with those beyond the threshold. As an example is the eye cataract. The somatic effects which occur in the exposed individual, genetic effects which occur in the progeny of the exposed individual due to chromosome aberration in the parent, and teratogenic effects of the unborn fetus irradiated in utero. So this is the cell, and we have direct radiation and direct effect and indirect effect. It causes primary damage. It causes two things. Either the cell repair, which is good, and this is most of the time happens, or it goes into two things. We modify the cell, or the cell die. If the cell die, this damage to the organ, death of the organism, and deterministic effect. If the cell is modified, we have two things, in somatic cells or the germ cells. In the somatic cells, this causes the cancer, like leukemia. If the germ cells, this goes to the hereditary, to the unborn, and this is the stochastic effect. Deterministic effect. A deterministic effect of radiation exposure is defined as the effect that increase in severity with increasing absorbed dose in the effect tissue, and usually has a minimum threshold value. Below this threshold, the effect is not seen. Deterministic effect attributable to exposure to ionizing radiation includes skin reddening, tissue necrosis, hair loss, cataract, blood abnormalities, and a decrease in sperm production in the male. Like for cataract, what is the threshold for cataract? Anyone knows? No? Eye cataract. Thin gray, Doris, this is correct. In the protocols, they are writing that thin gray will cause cataract, or the lenses are gone. Okay, let's start from 2.5 gray and above. From 2.5 gray and above, if the lens is directly irradiated to this may cause cataract. And you could see this easily with the people who are working with the fluoroscopy. Most of them have a problem with their lenses and so on. The threshold of deterministic effect, cataracts of the lens of the eye, from 2 to 10. This is what we said, Doris, 10 gray, and this is the protocol, but usually from 2 gray this happens. Yes, and geography the same. Thank you. Permanent sterility. For males from 3.5 to 6 sievert, we have permanent sterility. For females from 2.5 to 6, temporary sterility. For males we have around 0.15 sievert. For females we have 0.6 sievert. So the female are more radiation resistant to sterility than men. Note that the threshold may differ from one person to another. That's why it's coming as tolerance from 2. It's not fixed number. The stochastic effect. These effects, which are generally delayed or latent in nature, are defined as the effect in which the probability of occurrence, rather than the severity of the effect, is a function of radiation dose without threshold. So here we don't have a threshold. In the deterministic or non-stochastic, we have a threshold. Before that, nothing happened. In the stochastic, no threshold. It can happen in low dose, it can happen in high dose, and so on. Examples: cancers, solid malignant tumors, and leukemia. Heritable genetic effects are graded as the main stochastic effect from exposure to ionizing radiation. Heritable effects were considered most important in 1950s and 1960s. The somatic effect. This is a normal cell being exposed to radiation. The cell became mutated or the cell died. Biological effects that appear in the exposed person. Examples: cells become cancerous or cell death or cataract formation, increased susceptibility to disease, and somatic effect may result from either acute or chronic dose of radiation. The heritable effects from it, heritable, so it goes to the next generation. Biological effects that are inherited by children from their parents at conception. Irradiation of reproductive organs can damage, alter the cells involved in conception and can alter genetic information. Heritable health effects that have been observed in humans based upon animal data, and the assumption is made that heritable effect could occur in humans. So all the experiments being done in animals, and they make the assumption that this may happen in humans. Factors that determine the biological effect of radiation: area of the body exposed, cell sensitivity, individual sensitivity, types and energy of radiation. As we said, alpha is 20 times than that of photons. Total dose received, dose rate. The high dose rate, it means this is acute rather than chronic for a longer time. Relative sensitivity of the cell and tissue type. So we have lymphocytes, spermatogonia, hematopoietic, the blood forming. So let's see this sample. So these are most sensitive, and this is least sensitive. So the collagen is the least sensitive. Bone is least sensitive. Whether the lymphocytes is more sensitive to radiation. That's why for lymphoma, how much dose we are giving? Almost around 20 gray we are giving for the lymphoma usually. Whereas for the bone, like sarcoma and so on, we reach sometimes up to 70 gray because they are radio resistant. Could not hear you. Okay, I will repeat. I said, fine. For the lymphomas, usually we give around 20 gray, 25 gray because they are radio resistant, radio sensitive. Whereas for bone, like sarcoma and so on, we reach up to 70 gray because they are radio resistant. So we need more dose to kill such. Okay. Do you hear me? If you hear me, please type 1. Guys who don't hear, it seems there is some problem with your internet connection. So I'm sorry for that, but this is the best that we can do. It's not. Nerve cell is more resistant than the bone and muscle cells. Yes, you're right. The nerve cells are resistant, but not more than the bone and collagen. Okay? The nerve cells comes before. And you have to know that if it is well differentiated or non-differentiated, this is also a very important factor. So radiation sickness, we have the syndromes, different nervous system syndrome or CNS, cerebrovascular syndrome, gastrointestinal syndrome, the hematopoietic syndrome, and so on. I will not talk in details in this table because I think it's clear. You just need to look at it. Thank you very much for joining me, and we spent around 2 hours. And I think I did not really feel of it because of your joining and your participation. The presentation will be recorded, and I guess within 24 hours
you can download it, and I make it open for everybody so you can download it easily. And I will forward this presentation for you. I will upload it in the Dropbox so you can easily take it from there. And after that, we need to do quiz assessment. I think it's enough for today. What do you think? Enough for today, or you are enthusiastic to do a quiz with 20 questions? Okay, enough. I got it. Fine. Okay. We'll make it for, maybe we'll do it for tomorrow, because I just need to send you the link and you go through and you solve the quiz, and we see who's doing well. Anyhow, I know exactly every one of you how he answered in the poll, and I will wait till tomorrow after you finish the quiz, and we see who's the best doing, all of you, and the first three of you will get gifts as we promised. Okay, guys? I said I will put it in the Dropbox, this presentation, so you can easily download it. Sorry for a very long presentation. I was not really planning to take 2 hours, but I don't know. Time run very fast. And all the best for the people who will do the next, inshallah. Thank you, and have nice night or nice sweet dreams. See you. Thank you very much. Goodbye. Good night.